sir.
Hello, Marika. How are you doing?
I'm all right. How are you?
I'm doing all right as well. All right, that's good. Oh, did you get to finish the assignment?
Yes. You sent the homework and the worksheet. Is both of them? I did both of them.
Go
But
again?
you sent the worksheet. There was a worksheet and the homework. Is which worksheet?
Yes. Yes, I sent a worksheet, but I
Yes.
sent the answer with the worksheet, and then I sent the homework. The worksheet were the questions that we were going through.
Okay. Okay.
Yeah. All right. So
All
now
right.
today, this is what we're looking at today: binary operation. All right. Binary operation. And when we're doing binary operation, we're looking at binary operation on the real number system. All right? So the real number system. So before we get into binary operation, we have to revisit the real number system. So let's talk about the real number system. So the real number system, I know we looked at a little bit of it when we were doing complex numbers. It's the same thing. The real number system, it just starts with first natural numbers, which we say are counting numbers. So all the numbers that we count, like 1, 2, 3, 4, 5, going up, natural numbers. All right, those come naturally to us. Then whole numbers are the set of natural numbers plus the number 0. All right, that's all. So whole numbers, we just add 0 to it. And so we say that natural numbers is a subset of whole numbers. And then we go to the set of integers, and the set of integers, these are just now positive and negative whole numbers. So instead of just having these whole numbers, we can have the negative of these numbers, and now that set is known as integers. And so we said that whole numbers is a subset of integers, and also natural number is a subset of integers. All right, the symbol we use for integers is Z, a capital Z. The next thing that we have is rational numbers. And rational numbers is just a set of numbers that can be expressed as a fraction, either positive or negative fraction. All right, so even a number like 5 is a fraction because a number 5 can be written as 5 divided by 1. We can always write a number as 5 being divided by 1. And so 5 over 1 is also a rational number. All right, and so what we can conclude then is that integers are rational numbers, whole numbers are rational numbers, and natural numbers are rational numbers. All right, then the next thing that we have is what is known as irrational numbers. And irrational numbers is just a set of numbers which cannot be expressed as a positive or negative fraction. For example, the number pi. The number pi is 3.14159. Continue. We don't know what pi is. What's the exact value of pi? All right. Now look at your calculator, and there's a number called e, exponential e. Put in a calculator e and tell me what's the value for e. Tell me what you get for the value for e. So to find e on your calculator, it is, you see where you have ln, you have ln on the calculator beside log. You press the alpha button and then press ln, and that gives you the e. All right?
0, sir.
All right. So let me show you e. I'm going to turn on my camera for a second so I can show you the e. All right. Now, if you were to look at my camera right here, look at my camera. All right. This is ln. This is the ln on the calculator. So to get that e, what you're going to do is you're going to press alpha. So you press alpha. So I press alpha. And after I press alpha, I press ln. Then I press ln. After I press ln, that's the e. That's the e I'm talking about. All right. And then you press equal and look at the value that we get for e. 2.7185, and it continue and continue and continue. All right. And so what we notice is that there's no exact value for e. All right. There's no exact value for e. We cannot find an exact value for e, and so it's known as a irrational number. So e pi, the square root of 6, the square root of 29, these sorts of numbers are known as irrational numbers. Also, I won't be writing so well today, so I might write jumbly, like awful, because some stuff happened. So my apologies if you see me writing poor, but just pardon me for today and tomorrow.
Okay, sir, no problem.
Yeah, so I'm going to write real poor just for today and tomorrow. But I'll still try my best. So, all right, we have E now, and we said that E is 2 point something something. So E is also a irrational number. All right, E is also an irrational number. Now the set that contains all rational and irrational number is known as the set of real numbers. All right, so the set that contains all rational and irrational number is known as the set of real numbers. And so in set notation, we say that the real numbers is the union of our rational and our irrational numbers. And that's the set of real numbers. All right, easy. That's a set of real numbers. All right, now before we even get into binary operation again, there's something known as axioms of real numbers that is on the CAPE math paper. Axioms of real number is where they'll ask you some stupid stuff like show that, maybe they say show that the sum of two odd numbers is even, or show that the sum of two even numbers is even. Some stuff like that. They call them axioms of real numbers. And this is what they've observed. So the first axiom of real number is that they state that an even number may be represented as 2k. Now tell me why you think an even number can be represented as 2k.
Does it have something to do with the complex numbers?
No, nothing with complex numbers.
So it's
All
2
right.
times, so it would be 2 times whatever the number is.
Very good. 2 times whatever the number is. And 2 times any number will always be a multiple or a factor of 2, don't it? 2
Yes,
times
sir.
anything will always be a multiple of 2. So say
Yes.
k was 7. 2 times 7 is going to give us 14. And so what we can then conclude is that no matter what is the number, right, it's still going to be an even number once the number is being multiplied by 2. And so what we can conclude then is that 2 times any number k is said to be a even number. Because as you can see, 14 is 2 times 7. 7 is odd. When you multiply it by 2, we get an even number. So that's the first axiom of real number, that 2 times any number is a real number. So generally they say 2 times k. And k has to be a natural number. Now, if we can represent an even number as 2k, if you subtract 1 from an even number, you get an odd number. Or if you add 1 to an even number, you get an odd number. So you agree with the second axiom, right? 2k minus 1 or 2k plus 1. Agree with that?
Yes, sir.
Nice. So those are the first two axioms of the real number system. The next thing we're going to look at now is the sum of two even numbers. The sum of two even numbers is represented by 2k plus 2h. 2k plus 2h is how we represent the sum of two even numbers. So think of one even number, maybe 10. If you have an even number 10 and you add it to another even number 12, what they're saying is that when you add two even numbers, you're going to get an even numbers, because the 10 plus the 12, that's just 22. And 22 is just 2 times 11, don't it? 22
Yes,
is
sir.
just 2 times 11, which is even, because 2 times any number is an even number. So we can conclude that this is even. So in algebraic form, how they want to see it, in axioms, some number 2k plus another number 2h, you can just factor out the 2 to get 2 times k plus h. And so the sum of two even numbers is even. The difference of two even numbers is also even. Now you can just factor out the 2 and you get 2 times k minus h. Whatever k minus h works out to be, when you multiply it by 2, that's just an even number. The next axiom is that the sum of two odd numbers is even. That's why this odd in red is right here. I left it out. So the sum of two odd numbers is even. So 2k plus 1 plus 2h plus 1. Well, when you add 1 plus 1, you get 2. And so we're getting 2k plus 2h plus 2. So we can factor out the 2 to get 2 times k plus h plus 1. And so the sum of two odd numbers is odd. So if you think about it, we're adding the number 13 and we'll add it to another odd number. Give me another odd number.
15.
15, all right? So we add it and we're going to get 28. Now 13 plus 15, as we can clearly see, that's just 28. Now 28, that is even, that's just 2 times 14. 28 is just 2 times 14. And so what we can then conclude is that the sum of two the sum of two odd numbers is even. The next thing we want to look at is the difference of two even numbers. The difference of two even numbers is also going to be even. Because if we have some odd number 2k plus 1 and you subtract another odd number 2h plus 1, you're just going to get 2k minus 2h, and then the 1 minus the 1 cancel. And so this is the algebraic way, or the axiom way, of expressing that the difference of two odd numbers is even. All right, so far everything is working out to be even, but let's just continue. Then the product of two even numbers, they say, is also even. Because if you multiply two even number like 4 times 8, that's 32. 32 is also even. So if we multiply 2k times 2h, we're going to get 2 times 2kh, which is 2 times a number which is still even. Aha! Now here's one that is finally odd. The product of two odd numbers is odd. For example, 7 times 3, that's 21. So the product of two odd numbers is odd. So we have 2k plus 1 times 2h plus 1. That's 2 times 2kh plus 2k plus 2h plus 1. If we were to expand this out, this is what we would get. And so we can clearly see that this part is even. 2 times this is even. 2k is even. 2h is even. But then that plus 1 makes it odd. And so the product of two odd numbers is odd. All right? Now, if a is greater than b and k is less than 0, they say show that ka is less than kb. Now, this is a popular question that they repeat like 6 times in CAPE Unit 1 and the paper 2. And the reason for that is they're testing this axiom knowledge. They said to show that the product of two numbers with opposite signs is negative. So what that means is they're telling us that when you multiply a positive number times a negative number, the result is negative. So positive times negative give us a negative result. All right? All right, so that's cool?
Yes, sir.
Nice. So here's an example. It says if A is greater than B and K is less than 0, show that KA is less than KB. Now to show this, what we have to start with is say, well, if A is greater than B, we can subtract B from both sides to get that A minus B is greater than 0, don't it? From this, right?
Yes, sir.
Now if we subtract B from both sides to get A minus B is greater than 0, what they're telling us is A minus B is positive, don't it? Since it's greater than 0, it's positive, right? And then they tell us that K is less than 0. So they're telling us that K is negative. But by this rule, it tells us that the product of a positive number, A minus B, and a negative number, K, is going to be less than 0, don't it?
Yes, sir.
So we'll multiply the K times the A minus B, the result is going to be less than 0. So when we expand in K now using the distributive property, we get Ka minus Kb is less than 0. And so if we bring over the Kb now, we're going to get that Ka is less than Kb. This is a very popular proof question. Doesn't necessarily have to be this one come, but I guarantee you they're going to ask something with this here. So always remember that the product of two numbers with opposite sign is negative. All that means is a positive number times a negative number is negative. All right. Now the next thing after we go through the axioms of real numbers is to just review some basic stuff on the real number system and the arithmetic operations. So for example, we have an arithmetic operation is said to be commutative if the order in which the operation takes place does not change the result. So we looked at this when we were looking at reasoning and logics. You remember? We said that the same way we said P and Q is the same as Q and P. Now the same thing apply now to the number system. If you have two numbers, it don't matter which the order in which you add them. A plus B is equal to B plus A. So we say that it's commutative under addition. So we say that addition is commutative. A times B is the same as B times A. And here I use an example, 3 plus 5 is the same as 5 plus 3. Now what I want you to notice is that subtraction and division are not commutative. Tell me why subtraction and division is not commutative.
Because you wouldn't get it wouldn't be the same.
Exactly.
So it wouldn't be the same.
Yeah, it wouldn't be the same. So we have a number 10 minus a number 5. 10 minus 5 is not the same as 5 minus 10, right? 10 minus 5 will never be the same as 5 minus 10. So clearly we can say that it is not commutative. 10 minus 5 can never be 5 minus 10. So we say, okay, not commutative. Simple as that. All right? It's the same thing with division. 10 divided by 5 is 2. 5 divided by 10 is a half. So it's not commutative. Very good. The next law is associative law. And associative law in the set of real numbers states that A plus B plus C is the same as A plus B plus C. What that means is the order in which we add the first two numbers, then add the third number, it wouldn't have mattered if we add the last two numbers, then the first one. All right? So it wouldn't even matter if we add the first number and the last number and then add the second number. All right? So the order don't matter in which we add. So for example, 3 plus 5 plus 2, we add the 3 plus the 5 to get 8, and then the 8 plus the 2 to get 10. Now, if we were to add the last two numbers, the 5 plus 2, we get 7. Then the 7 plus 3 give us 10. But what we can clearly see is that we get 10 on both sides, but no, look there. That's associative because the order did not affect anything. In the same way, for multiplication, A times B times C, we can write it as A times B times C. It doesn't matter the order. For example, 5 times 4 times 3. 5 times the 4 is 20. 20 times the 3 is 60. Now, if we were to say 5 times 4 times 3, 4 times 3 is 12. 12 times the 5 is 60. So it still gets 60. And so multiplication is said to be associative. All right, so again, these are the two rules that we have to remember, that addition and multiplication is associative. Likewise, subtraction and division is not associative because the order does matter for these. The next one is distributive law. Tell me what the distributive law is.
You can put, like, for example, if it's a negative number, you can put the number in brackets and then put the negative number outside of the brackets.
Go
And
again,
then,
so you're saying you put like a negative on the outside?
yes, so you can times the negative number by the number inside the bracket.
Yes, that's an example of distributive law. So for example, we have negative bracket x plus 1. This is just working out to be minus x minus 1. All right, and the reason for this is that this negative outside really symbolizes minus 1. So minus 1 times x plus 1. So let's get into that now. That's what we're going to talk about next. Distributive law. Now the distributive law, there are two ways distribution takes place. Distribution is such that multiplication takes dominance over addition. Multiplication takes dominance over addition. So what that means is that A times B plus C, it's equal to A times B plus A times C. So the best way of putting it is this. All right, so this is how we're going to see it more often than not. A in bracket B plus C. A in bracket B plus C. That's how more often than not we're going to see. We're not going to see the multiplication sign. And this is the same as AB plus AC. This is known as distributive law. And what it's telling us is that multiplication distributes over addition. So that's the distributive property. All right. So for example, if we have, it also works if subtraction was inside this bracket, it would just be A times B minus A times C. So practical examples of the distributive law is maybe we have 5 in bracket 3 plus 4, 5 in bracket 3 plus 4, and that would just be applying the distributive property. We would get that this is 5 times 3. This would be 5 times 3 plus 4 times 3. That's what the distributive property says. Ouch. 5 times 3 plus 5 times 4. That's what the distributive property says. So since we have 5 times 3 plus 5 times 4, that's just giving us 15 plus 20, which is 35. Now, if you were to just add 3 plus 4, you would get 7. And so you'd just be working out 5 times 7. But 5 times 7 is just 35. And so what we notice is that we're getting the same result. 5 times 7 is 35. And it's the same as 5 times 3 plus 5 times 4. And so this is known as the distributive property. All right, that's distributive property. Nice. All right. No, distributive property doesn't work if it's a division. All right, clearly it doesn't work if it's division. Division is non-distributive. It has to be multiplication. All right, that's the only time distributive property works. Now, the next thing we're going to talk about is identity. Identity of real numbers. What do you think identity is?
If it's a negative or a positive?
Not necessarily. So for example, I want to link it to real life. So when people say, who would you say your identity is? Your identity in reality is who you are no matter what, right? No matter what is happening in your life, you know how you define yourself. That's your identity, right? And so that's how we define identity in real life. Now, when it comes on to the real number system, so for example, now the identity of addition is 0, because what we're saying is which number, when you add it to a number A, it doesn't change it. You still get back the original number A, right? And so that number is 0. And so we say 0 is the identity for the addition of numbers. All right, so identity is that number such that when you carry out a particular operation, it doesn't change the number. All right, so repeat for me what identity is.
Identity of an operation is the number which leaves original number unchanged.
Very good, very good. That's identity. All right, so it leaves the number unchanged. So each operation have a different identity. So for addition, a plus 0 equal a, or 0 plus a equal a. And so we say 0 is the additive identity of any number. All right, now for any number, we just express as some number a. For multiplication now, what we're saying is that for multiplication, the identity is 1. Which number, when you multiply it by a, it will not change the result. That will only be 1. And so we say that 0 is the additive identity of any number a, and 1 is the multiplicative identity of any number a. The next thing we're going to look at is the inverse for addition and multiplication of real numbers. The inverse. So we look at the identity, and we're going to look at the inverse. Now the inverse is which number. The inverse is which number when it undergo a operation such that the result is going to be the identity. So for example, let's call the inverse a to the minus 1. All right, so let's call it a to the minus 1. Which number such that when I add to a, I'm going to get the result to be the identity. Now the only number that I can add to a such that I get the additive identity of a, that is minus a. And so we say minus a is the additive inverse of any number a. All right, so the identity is 0 and the inverse is minus a. That's the additive inverse, just for addition. For multiplication, I'm saying which number, when I multiply a times this number, I'm going to get the multiplicative identity, which we know is 1. So the multiplicative identity is 1 over a, because a times 1 over a is 1. So this is how we get a to the minus 1 is the inverse. So many people, just when they hear of inverse, the first thing come to their mind is a to the minus 1. A to the minus 1 is just the multiplicative inverse. All right, there's additive inverse different from multiplicative inverse. All right. So again, just to repeat it, when you talk about identity, which number, when I add to this number a, I'm going to get the result to be a. All right. And so the only number this can be is 0. And so we say that 0 is the identity. 0 is the identity, the additive identity. All right. When it comes on to inverse, you're going to say which number, when I add it to a, the result will be the identity. The additive identity is 0, and so the only number I can add to A to get the result to be 0 must be minus A. And so minus A is the additive inverse. Minus A is the additive inverse, all right, of addition. 1 over A is the multiplicative inverse, all right? And that's that. Finally, the next thing to talk about is closure. Now, what is closure? Well, closure is pretty simple. Whenever I carry out an operation and the result falls within that set, we say that the set is closed. So for example, let's say for example, 5 plus 10, right? 5 is an element of natural number. 10 is a natural number. When I add two natural numbers, the result is still a natural number, don't it? Right?
Yes, sir.
So when you add two natural numbers, the result is always a natural number. And so we say the set of natural number is closed. We say the set of natural numbers is closed. So, all right, that's what closure is. So for example, let me put it right here. We have 5 plus, let's say 10, right? The result is 15. But 5 is an element of natural number, but 5 and 10 are natural numbers. 5, 10, and 50 are all natural numbers. And so we say that because the result 15 is inside of the set, we say that the set of natural numbers is closed. So natural numbers is represented by n, and so we'd say that the set of natural numbers is closed. All right, now look right here now. Now right here I have 3 minus 7. 3 is a whole number, don't it?
Yes, sir.
And 7 is a whole number. But 3 minus 7 is negative 4. Is negative 4 a whole number?
No, sir.
No. And so we say 3 and 4 are real numbers and also whole numbers, but minus 4 is not a whole number. And so what we then can conclude is that the set W, the set of whole numbers, is not closed under subtraction. Same thing, if we divide two whole numbers, 9 divided by 2, we get 4.5. But 4.5 is not a whole number. So what we say that is the set W is not closed under subtraction and division. All right? So in general, this goes for most sets. Whole numbers, natural numbers, all right, integers, their results are never closed under subtraction and division. All right, and this is why a lot of times we find that when you're doing subtraction and division, they are not commutative and they're not associative. And this is the reason, because in general the whole set is not closed under subtraction and division. All right, so closure does have to do with the fact that the result also come from within the set that the elements were taken. All right. All right. Now the next thing to talk about is Cartesian product. What's Cartesian product? Cartesian product is just simply, what's the word I want to use? Coordinate system, as some would know it as. So for example, Cartesian product that we're used to is x cross y, where we have an x-axis cross a y-axis, right? And that's what we're used to. That's the regular Cartesian product we're used to, a x and a y. All right, so consider two sets, set A and set B. All right, so in functions, we learned that our set A, which is the x-axis, is the domain, and our set B, which is the y-axis, is our range. Now take away functions now, and you just keep it plain and simple. Cartesian product. All right, so everything that are inside of A, all right, So if A is an element of A and B is an element of B, then we write the set of all ordered pair AB, and these are called the Cartesian product. All right, those are known as Cartesian product. Why do we need to know Cartesian product? We need to know Cartesian product such that if they ask you, what is A cross B? There are many possibilities that can be for A cross B. A cross B just means that the first element is going to come from our set A and the second element going to come from our set B. So for example, we can take the first element 1 from this set, and then we can take A from set B. So 1A is an ordered pair. We can take 1 from set A, or we can, and then we take B from set B. So we have 1B, and we can continue to get all these set of ordered pairs for A cross B. Now B cross A, the order switch around now. And so the first element have to come from B. So the first element in this part right here, A, B, or C, that has to come first. Then 1 or 2 gonna come last. Then you can also have A cross A, where you take both elements from the same set. So 1, 1, 1, 2, 2, 1, and 2, 2 is A cross A. So Cartesian product, that's understood?
Yes, sir.
Nice. So that's Cartesian product. Now the next thing that we're going to talk about is binary operations. Finally, we're at binary operations. Now, binary operation. What is a binary operator? A binary operation on a non-empty set A is defined such that A star B equals C, where A, B, and C is element of set A, and star is a function which maps the ordered pair. So pretty much what a binary operator is, it's just an operator that combines the 4 basic operations together. All right, it's just a connector between 2 real numbers. That's what we're going to be looking at. So for example, if they tell you that x star y is 2x plus 2y, what they're telling us now is that some number x and some number y are connected by this operation. So for example, let's say that x star y, they don't even need to use star as the binary operator. They can use any symbol. So say they use a triangle. They say x delta y, that's what the triangle means. X delta y, it's equal to 2xy. Let's say this is an example. What they're telling you is that whenever we're given some number to carry out to find the binary operator of this, so let's say they want 3 delta 5, what they're telling us is that the first number and the second number are connected by this operation. And so 3 delta 5 will just be 2 times 3, because your x is 3, look at your x as 3, and your y is 5. And so that would be 3 delta 5. So what a binary operator is, it's just a connected operation system pretty much, which connects the 4 basic operations such as addition, multiplication, subtraction, and division. That's all a binary operator is. All right? So here it is, the 4 basic operation on the set of real numbers: addition, subtraction, multiplication, and division. All right. Now the next thing is properties of a binary operator. Now the same way how we did look at properties under the real number system is the same way they follow for binary operators. We said that a binary operator star is commutative if A star B is B star A. Now I highlight it because we must remember this. Anytime they give us a binary operator star and they ask you show that it is commutative, this is the first thing that you do. You check to see if A star B is equal to B star A. All right?
Yes,
All right,
sir.
that's fine. Nice. So this is the first thing that we have to know about binary operators. All right, so star is commutative if and only if this happens. All right, so the same way how we know that addition is commutative and multiplication is commutative, we can also check to see if binary operators are commutative. The next thing to check for is if it is associative. So if a binary operator is associative, the order in which you carry out the operation does not matter. And so A star B star C is the same as A star B, then the result star C. So A star B star C, you work out B star C first. That's what this bracket means. You work out B star C first, and then A star this result, if it's equal to A star B, and then this result star C, we'll say that it is associative. All right? That's when a binary operator is associative. So we need to remember this formula. This is a must know. We have to know this. We have to. This is a must know. Right here for when it is associative, this is a must know. We have to know this. All right. Now, the next one to look at is distributivity. Now, when we're talking about distributivity, it's the same way when you think of multiplication outside here and an addition or a subtraction inside here. So now what we say is that star is distributive of another operation delta if and only if A star B delta C should work out to be A star B delta A star C. So think of your star as multiplication. The same way how you'd have 5 times 3 plus 2, we'd say that this is distributive because it works out to be the same as 5 times 3 plus 5 times 2, don't it? 5 times 3 plus 2 is the same as 5 times 3 plus 5 times 2. And so the same way we can say that the operation star is going to be distributive over delta. If when we work it out, we get A star B delta A star C. All right, and that's when a binary operator is distributive. All right. Now, the next one we want to talk about is identity. Don't worry, we're going to do lots of examples afterwards because binary operation is the shortest topic on Cape Math. So binary operator next is talking about the identity. So remember, the same way how we add identity, and we said that the identity is any number such that when it undergo the operation, the result should give us back the original number. So the same way that for a binary operator star, when it undergoes the operation star on some number A, if the result gives us A, then the other number E is known as the identity of star. All right? So in order to find the identity of any binary operation, we solve the equation A star E equal to A. So in order to find the identity of any binary operation, we solve the equation A star E equal A. So we solve A star E equal A. A star E equal A, where E is the identity. E is the identity. All right. So we solve the equation A star E equal A, where E is the identity. After we solve this equation, we're going to transpose and make E the subject, and that's the identity for the binary operation. All right. Don't worry, we're going to look at other examples. So this is just an example for the notes. Then inverse. For inverse, sometimes I call it A to the minus 1. Another time I call inverse I. Don't call it A to the minus 1. And there's a reason why I don't like call it A to the minus 1 all the time. Let's call it I. So the inverse of a binary operation, I, to find the inverse, it is whenever the operation star undergoes on some element A, and the result gives us back the identity, then that element I, or a to the minus 1, is known as the inverse of the binary operation. So what we're saying is that in order to find the inverse, we solve the equation a star a to the minus 1 equal e. So we solve a star a to the minus 1 equal e, and this a to the minus 1 is the inverse. You can call it I if you want. Any letter suffices. All right? And that's it. This is just an example now. And that's it for binary operation. That's all the notes for binary operation. Binary operation short, don't it?
Yes, it is.
Yeah, very short. Binary operation is very, 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 very short. All right, nice. So now what we're going to do is just do lots of examples now. Lots of examples. All right. So this is a worksheet we're going to go through today. And this is a worksheet that I gave my students recently. But this is a worksheet I'm going to send to you as an assignment. All right, you're going to get this one as an assignment. 10 question due next week, Friday. All right. So you said you sent me your assignment, so I'm going to mark it and send back the result to you. All right.
Oh, yes, sir.
And I'm going to send you the result with the solution as well.
Okay.
All right.
When I was doing the assignment, I had issues with algebra proposition.
Algebra proposition.
Yes.
All right, no problem, no problem.
Also, sir, I'm trying to get into a university, and I don't know if my grades, if the grades for CAPE will come out as quickly, because the deadline is in July, I think, July or March.
Oh, so you want to start university January?
No, not January. It will be next year, September.
Yeah, next September. Yeah.
Yes. So the school is saying that if you don't have your grades out as yet, they're saying that you should have a report card with like your last two report cards showing like your grades and stuff. I spoke with Quality about it, and they said that if I'm getting any sort of like graded assignments,
yeah,
or just assignments that could just add to the report card, anything with grades.
Okay. So you want me to submit the grades to them?
Yes. So anything like, I don't know, I guess give me a test or something, I don't know, and then you can grade it.
Yes. All right, no problem. Definitely.
Okay.
All right. Nice. We can do that. All right.
Okay.
So what
thank
I'll
you.
do is I'll give you a test to do after binary operation. So I'll combine the two topics and give you a test.
Oh, binary operation
And reasoning and logic.
Okay.
All right. Nice. All right. So give me a second. Let me plug in this laptop. All right, let's go. So this question number 1, we're going to start with. It says that A star B is equal to A plus B plus 5. And it says that show that the set of real numbers is closed with respect to star. All right, so what they're asking you to do is to pretty much show that star is closed. All right, how would you show that this is closed? What's coming to your mind?
Is it associative?
To show that it's closed. So what does closure mean?
I don't remember.
All right, now closure, what we pretty much said is whenever you have an operation A star B, all right, whenever the result is also going to be element of that set, then we can say the set is closed. So it tells us that A, so what they tell us is that star is defined on the set of real numbers. So when star is defined on the set of real numbers, what they're telling us right here is that A is a real number, A is an element of real, and B is an element of real. That's what they're telling us. A is an element of real, and B is an element of real. Now, if A is an element of real and B is an element of real, A plus B, when you add two real numbers, what you're gonna get? When you add two real
You
numbers,
get a real number.
you get a real number. Now, when you add that real number to plus 5, what you gonna get?
You also get another
Still
real
get a real
number.
number, so hence you can say that yes, the set of real numbers is closed with respect to star. So that's how you do that question. So let's write down the solution. Let's copy this question and we're gonna do this one first. Very easy. Where the question happened to go? Bring this over. All right, so A star, the binary operation star is defined on the set of real numbers such that A star B is equal to A plus B plus 5. Show that star is closed. Find the identity, and then given any element, find its inverse. So let's do this question. This question we're going to tackle together very easily. So now again, as we said, they said star is defined on the set of real numbers. So the solution for part A is we're going to say A and B are real numbers. A and B are real numbers. All right. And then we're going to say A star B it's actually equal to A plus B plus 5, and A plus B plus 5, all of this is going to be a real number. And so we're pretty much finished. So then we can write our conclusion now, and we can then conclude that. So now we can conclude, hence, star is closed under the set of real numbers. All right, once the result is also from the set of real numbers, then we say that star is closed. All right, that's what closure means. Now part B says find the identity element. How are we going to find the identity element?
When that's when it's equal to the number, right? So like
Yes.
So it would be
All right, so we just need to remember this equation. we solve A star E equal A. All right? A star E equal A. We use to solve this equation to find the identity of any operator star. All right? So whenever anytime you have any element A undergoes the operation star, once you get back the original result, then this element E is known as the identity of A and the identity of star. So now let's do that. So now let's say we have A star B. Now look at this. A star B is A plus B plus 5. So what's A star E going to be equal to?
A star E.
Yes.
It'd be A
A.
star B.
All right, so what I'm saying is A star B is A plus B plus 5. That's A star B is A plus B plus 5. So what I'm then saying then is A star E is going to be replace B with E. And so A star E is A plus E plus 5. You see that?
Yes, sir.
And that is equal to A, don't it? Because A
Yes.
star E is A, right?
Yes, sir.
Nice. And so what we then get is that we need to make E the subject. So let's make E the subject. So to make E the subject, we can subtract A from both sides and then subtract 5. And so we're getting E equal negative 5. Can you see that?
Yes, sir.
E equal negative 5. And so E equal negative 5 is the identity. All right? So E equal negative 5 is the identity. And we're done. Easy. E equal negative 5, that's the identity. So we can say that is the identity is minus 5. So that's the identity of star. All right. Now part C. Now part C, it says given any element A, find its inverse. What was the equation that we used to solve for inverse?
A to negative 1.
Very good. A star A to the negative 1. And I'm going to use, not going to use A to the negative 1. I'm going to use I. I represents inverse. So A star I equal
1.
E. That's the equation that we use. A star A inverse equal E. And then we're going to try to find I now, and I is going to be the inverse. So then what's A star I? What's A star I?
A plus I plus 5.
A plus I plus 5. Very good. And that's equal to E. But what's E?
Negative 5.
Negative 5. Very good. So now we just need to make I the subject. Make I the subject and tell me what you get for I.
I is equal to negative A.
I is equal to negative A.
Because you're making it the subject, right? So
Yeah, make it the subject. So I is equal to negative A. That's it.
plus negative 5.
Plus negative 5.
Plus negative 5.
Plus negative 5. So I is just equal to negative A minus 10, right?
Yes, sir.
And that's the identity. Nice. So that's the identity. We're done. And so we can conclude that is the identity. So we can conclude that is the identity, that is the inverse, rather, the inverse is minus A minus 10. So that's the inverse. That's it. So the inverse is minus A minus 10. And that takes care of question 1. Very easy. All right. So here we have it again for question 1. So for question 1, we showed that A plus B plus 5 is also a real number. And so hence we can say that the set is closed. We just use the formula A star E equal A to find identity and transpose to make E the subject. And then we use the formula A star I equal E and make I the subject to find inverse. All right? Easy, very easy question. Nice. So let's look at another question now. Let's look at question 2. I'm just saving them from now so it's easy to share the document. So let's look at the second question. Second question, question 2. So question 2, it says, two binary operators star and black box are defined on the set of real numbers. A star B is equal to 3 times A plus B, and A black box B is 2 times A times B. Show that one of these operators is associative. So one of them is associative, not both, just one of them. So one of them is associative. How are we going to show that one of them is associative? What's the associative rule?
That you can multiply or add in any order.
In any order. So in terms of binary operation, what's the associative rule? All right, so in terms of binary operator, the associative rule is pretty much to show that the order in which the operation is taking place doesn't matter as well. All right, so all right, this still need to edit it down a little smaller. All right, this should make it fit. What? All right, that's crazy. All right, so let's show that one of these is associative. So what we have here, again, we have that A star B is 3 times A plus B. So to show, let's start with trying to show that star is associative. So to show star is associative, so I'm just gonna write, I use ASS full stop to represent associated. To show star is associative, we need to show that A star, B star, C, the order doesn't matter. So what we're saying is A star, the result of B star C, should give us the same result as if we were to take A star B star C, where we start with finding the result of A star B first, A star B, and then take that result and star C. All right? So So that's how we prove associativity. Nice. So that's how we prove associativity. All right. So this is what we do to prove associativity. So let's see if we can prove that now. So to show that star is associative, we need to show that this equation is true. So now, let's start with the left-hand side. So we start by saying our left-hand side is equal to A star B star C. What's A star B star C?
It'd be 3 times A plus 3 times B.
All right, so that's A star B. So now, when we're working out A star, B star, C, you always start with the bracket. All right? You always start with that bracket. So what we're going to start with is put back our A star. But now we're just going to work out the bracket, B star C. Now what is B star C?
Would it be A plus B?
B star C means B star C would be 3 times the number B plus the number C. So replace A with B and B with C, all right?
Okay.
All right, so that is fine. So replace A with B and B with C. And so B star C in this bracket is just 3 times B plus C. Good with this? That's fine?
So when the law is, it would be A star bracket B star C, and you'd have to put, since you're working out the bracket first, you'd have to replace A star B with B star
B
C.
star C, yes.
Okay.
Yes. So let's say they give you actual numbers. A star B is 3 times A plus B. What if I ask you what is 5 star 2? What would be 5 star 2?
Put it where, can you repeat it?
Yeah, so what if I'd ask you from up here, what if I'd ask you what is 5 star 2?
5 star 2. It'd be 3 bracket 5 plus 2.
Very good, that would be 5 star 2. 5 star 2 would be 3 bracket 5 plus 2. So the same way A star, B star C is just going to be A star, the result of what is B star C. Result of B star C is 3 times B plus C. All right?
Yes, sir.
Nice. So what we're getting now is that A star B star C is equal to A star, now 3 times B plus C is the same as 3B plus 3C. You agree?
Yes, sir.
Nice. So now, what is A star 3B plus 3C?
It would be A times 3BC.
It would
So
be
it'd be
3 times,
3BA.
it would be 3 times
3 times 3BA.
it's going to be 3 times A plus 3 times A plus, so it's A plus. So it's like now you're replacing your A star 3B plus C. You replace your A with A, and then you replace this B with 3B plus 3C. So it becomes 3 times A plus 3B plus 3C. All right, so it's 3 times A plus 3B plus 3C. And all of this simplifies to be 3A plus 9B plus 9C. All right, and that is A star B star C. All right, you understand how I got the 3 times the A plus the 3B plus 3C?
I don't understand how you put is it that you just put A into the bracket?
All right, so all I did was, all right, let me try and use a marker. So all I did was right here. All right, so right here now, A star B is 3 times A plus B. So what binary operation mean is that it is telling me some number, some first number is connected to the second number by this equation, 3 times A plus B. So what that means is anytime I'm given two other numbers, maybe 5 star 2, it's just going to be 3 times 5 plus 2. If I'm given 10 star x, what's 10 star x?
10 plus x.
It wouldn't be 10 plus x, it would be 3 times 10 plus x. All right? That's the operation that connects the two. So 10 star x, so 10 star x would just be following A star B because this is how the numbers are connected. So 10 star x would be equal to 10 times, not 10 times, 3 times 10 plus x. That would be 10 star x. So what I'm telling you pretty much is any number what they give you to work out, let's say you're working out C star E. C star E, what would be C star E? What would be
It'd
C
be
star E?
3
Yeah?
bracket C plus E.
C plus E, very good. That's all is C star E. So no matter what what operation you're carrying out, this is how two numbers are connected for this binary operator star. All right, it's just 3 times the sum of the two numbers. That's all that is saying. All right, that's all that is saying. So that's why now right here we have that A star, B star, C. When you see a bracket, you work out the bracket part first. Always work out the bracket part first. Always work out that bracket part first. So I'm gonna put it in bold. Put it in bold because we always work out this bracket part first. That's what we learned from primary and prep school. So when we work out B star C first, what would be B star C?
3 times B plus C.
Yeah, that's B star C, 3 times B plus C. And so then now that result, we're going to find now A star, the result in here, because what we're saying now is that, let me push it down a little bit. What we're saying then is this. We're saying now that A star, B star C is the same as A star, B star C is this, 3 times B plus C, right? And all of that simplifies now to just be that 3 times B plus C is 3B plus 3C. So now all we need to work out is A star 3B plus 3C. All right? That's all we need to work out now. A star 3B plus 3C. All right?
Yes, sir.
Nice. So that's all we need to work out. So since that's all we need to work out, what we're solving now is A star 3B plus 3C. Now what is A star 3B plus 3C?
3 times A plus 3B plus 3C.
Very good, nice. And that's how we end up get this. And so the result is 3A plus 9B plus 9C. Very good. Now to prove associativity, we need to then show that the right-hand side should give us that same result. So now we're going to work out what is A star B star C. We're going to work out this result now. So we're going to work out what is A star B star C. Now, what we do is work out first what is A star B. What is A star B? Yeah, what's A star B?
It would be 3 times A plus B.
3 times A plus B. Very good. That's A star B. And that result, we're going to start with C. So this simplifies now to just be 3A plus 3B. And that result, we're going to start with C. Now what's 3A plus 3B star C?
3 times 3A plus 3B plus, no, 3 times 9A
3
plus 9,
times.
3 times 9A
How you get 9A?
is not going to be 3 times 3A.
It's going to be 3 times. Oh, you're expanding it all the way out already.
Oh. So, okay, so don't expand it as yet.
Don't expand it as yet. No, don't expand it as yet.
So 3A plus 3B plus C.
Very good. 3 times 3B plus C. Then after you close up that bracket, then expand it out. All right, your 9A plus your 9B plus your 3C. Now
So
start.
the reason why C is added into the bracket is because originally it was A star B equals 3A.
Yes.
Okay.
Yes.
So you always
Nice.
have to look back at the original one using
Yes,
the
you
identity
always
as
have
well.
to look at the original one to work out what you need.
Okay.
Brilliant. Nice. So now what can we conclude? Can we say that star is associative?
No.
Is star associative?
No, it's not.
No, it's not. And it's not because these two are not equal, don't it? They're just not equal. So because they're not equal, clearly we can see that star is not associative. So they're not equal, so star is not associative. What happened? What did I do? Ah, I see what I did. I shouldn't have done that. Yeah. All right, so star is not associative. Star is not associative since it's not associative since A star B star C is not equal to A star, working out A star B star C. So that's why it's not associative. All right. So we prove that the first one is not associative. Let's check if the one with the box is associative now. All right. So let's check if the one with the box is associative. All right. Now the one with the box is that we have A box B is equal to 2A. It's equal to 2A plus 2B. So A box B is equal to 2AB. So let's try to find out if box is somehow associative. So to show if box is associative, we need to show that A box B supposed to work out to, we need to show that A box B box C so we need to show that A box B box C, working out B box C first. We need to find out if this is going to give us the same as working out. Put the bracket around A box B box C, right? That's what we need to show if this is associative, right?
Yes, sir.
Nice. So let's work out the left-hand side first. So the left-hand side, which we know is A box B box C. So let's work out now. So we always start with the bracket. So we get A box. What is B box C?
It would be 2
2
BC.
2BC. Very good. That's B box C. So now what would be A box 2BC?
It would be 2 ABC.
2. All right, so now it's going to be 2 times, it's 2 times the first number, which is 2 times A, times the second number. And the second number is what? 2BC. So it is 2 times A times 2BC. All right?
Yes, sir.
Nice. And so what this simplifies to be is 4ABC. Now what we need to now work out is our right-hand side. Our right-hand side, which was A, let me copy our right-hand side. Our right-hand side is A, our right-hand side is A box B box C. So working out A box B first. What's A box B?
2AB.
2AB. So now we need to work out what's 2AB box C. So we need to work out 2AB box C. Now what's 2AB box C?
2C times 2 times C times 2AB.
Very good. So it's really 2 times our first number. Replace our A with 2AB times our second number, which is C. And so this works out to be 4ABC. Now what can we conclude about box?
That it's associative.
Box is associative. So we can conclude box is associative since both are equal. So box is associative. Associative, not spelled right, but oh well. So box is associative. All right, and we leave it right there.
Sir, when you go to edit, you ever try to click on done and see what happens?
Click on down.
Done.
Click on done.
Gives you it gives you options. So once you go and edit, you see done.
Oh, I don't know. Let me try. Oh, done. Oh, done. Don't. Done.
Oh,
Don't.
so when you go to edit,
Yeah.
and then you go back,
Go back.
yeah.
Like click this back.
No, like go back to the edit mode.
Go back to the edit. It's not giving me anything.
Oh, can you save it?
Yeah, I can save it. I can save it. It's going to be saved. So I'm going to save it as Q2.
So what's that save button? That save button beside the back arrow at the top?
Oh, this?
Yeah.
Ah, save as Q2. All right. All right, so I'm just trying to fill all the space now. Yep. So this is it, all the questions showing now. Yeah, so that's it. So we've shown that this one is associative and this is question 2. All right, so now let's look at next question, question 3. Question 3 says, the binary operation star on the set of A, where A is a real number, but it is positive, A is always greater than or equal to 0, is defined as A star B is A minus B all square for all A and B are element from the set A. It says show that A is closed with respect to star, find the identity for star, and then find the inverse, and then determine if star is not associative. All right? So let's tackle this question. Let's tackle this question. So this looks fairly easy. Right, no, it's not going to show when it's so much. The binary operation star is on the set A and is defined as, push that down, A minus B squared for all A and B is in A, show that, and then B, C, then option B. All right, and we should do it now. All right, so the first part says, show that A is closed. How are we going to show that A is closed?
We have to show that is a real number, and the operation, you'd also get back a real number.
All right, so to show, as you said, we need to show that when we work out A minus B all square, we need to see that that result is a real number. We need to show that the result that we're going to get from A minus B all square is going to be a real number, as well as it's going to be greater than or equal to 0. All right? That's what we're going to do for that question. We need to show that A minus B is going to be, A minus B is going to be inside this set A. That's the only way the set is closed, is if this result is going to give us a real number such that it is also greater than or equal to 0. So let's do that question now. All right, so let's start with again with A star B, right, is equal to A minus B all square. That's A star B. A star B is A minus B all square. Now, where it tells us that A is greater than or equal to 0. A is greater than or equal to 0. And also, A is an element of real number. A is real number. Now, if A is a real number, then look what happened. Now, A is a real number. B is also a real number. All right, because they're saying for any element inside this set, it's a real number and it's greater than 0. So also B is also greater than or equal to 0. All right, and B is also a real number. So we can say A and B is a real number. Now, what is going to happen then? What's going to happen then is that we have a real number. So we have a real number A and a real number B. Now, when we take the difference of a real number, A minus B, right? A minus B, and then we square it, that's always going to be greater than or equal to 0. Tell me why this is so. This is always going to be greater than or equal to 0. Tell me why that is.
Because it's being squared by 2.
Very good, it's being squared. So no matter what A is and B is, once you square it, it's going to be positive. The square of all number is positive. The square of all number is positive, and so since the square of all number is positive, what we can conclude then is that hence, since the square of all number is positive, then we can conclude that A minus B all square is also a real number, and that real number is always greater than 0. So star is closed. Star is closed. All right, so for example, say B is negative 20, and say A is 35. 35 minus 20 is squared, that's 225. A is 100 and B is 175. 100 minus 175 is 75. Then that 75 square give you 5,625. So no matter which number you choose for A and B, when you square it, the answer is going to be greater than or equal to 0. Can you agree with that statement?
Yes, sir.
Nice. And so we say that A is closed. Now, how are we going to find the identity? It says find the identity. How are we going to find the identity?
So it would be
What's
A
the
star
equation that we
B,
solve for identity?
A star E is equal to A.
Yes, A star E is equal to A. We solve A star E equal to A to get the identity. So what is A star E?
It would be A minus E
Yeah,
squared by 2.
squared. Very good. A minus E squared, and that's equal to A, right?
Yes, sir.
So we have A minus E all square is equal to A. So how are we going to make E the subject from this? How are we going to make E the subject?
First you have to square
Very
them.
good. So square root, we have to square root. Because once we square root both sides, we then get A minus E is equal to the square root of A. A minus E is the square root of A. All right? So that's what we get now. So now we can make E the subject. So when we make E the subject, we're getting that E is equal to, when we bring over that, we're getting E is equal to A minus root A. Can you see that?
Yes, sir. But
All right. What
wouldn't
I did
A be
was bring over the
negative?
E. Repeat.
Wouldn't A be negative?
Yes, root A is negative, because what I did was I bring over the minus E to this side, and then I bring over the root A to the other side.
So, okay.
Make sense? Yeah. So that would be the identity. All right. So that's the identity. So you just tell them hence the identity. So let's write that for them. That is the identity. So that's the identity. All right. Now let's look at part C. Part C wants us to find the inverse. How are we going to find the inverse?
A to the negative 1.
What's the equation we solve for to find inverse?
A to the negative 1.
A to the negative 1. I don't like to really say A to the negative 1. We're just going to call A to the negative 1 I. Let's call it I for now. So we're solving A star I equal
I.
equal E. A
Star
star I
E.
equal E. All right, so that's the formula we use to find the inverse. A star I equal E. All right, so then what is A star I?
A minus I
Yeah,
squared
yeah, and that's
is equal to E.
equal to E. And E is just A minus root A. So this is E, A minus root A. So we're going to make I the subject.
You have to square root that
We have
side.
to square root both sides. So when we square root both sides, that tells us that when we square root both sides, we're getting A minus I. We're getting A minus I, and that's equal to, we square root both sides to get A minus I is the square root of A minus the square root of A, right?
Yes, sir.
Nice. So now to make I the subject, we bring I over here and bring this part over here to get that I is equal to A minus all of that. So I is equal to A minus the square root of A minus root A. All right? A minus the square root of root A. All right? And that's how we find the inverse. All right, so it's just a bunch of formula and equations to remember, and we're good. Once we remember the equations, we're good with binary operations. So that is the inverse. That is the inverse. So that's how we find the inverse. All right. Now that we find the inverse, the last part of the question said, determine if star is associative. How are we going to determine if star is associative? What's the equation we should to show star is associative?
A star bracket A star B close
Yeah,
bracket star C,
yeah.
and then A star open bracket B star C.
Very good. Very good. Brilliant. That's how we show that star is associative. So let's check it out. Let's check out if star is associative. So to check out if star is associative, we work out A star B first. What's going to be A star B? This is the left-hand side.
It would be A minus B.
A minus B all square, right? So that was our A star B. And that result, we're then going to start with C. All right. So let me just write out this time. All right. Please, finger, just hold up for a bit. All right. So A star B, as we said, that's just A minus B all square. And then we're going to start with C. Now we're going to start this result with C. Now what is A minus B all square star C? What's that equal to?
A, it'd be A squared
That's going to
and
be
A squared
A squared.
and B squared.
Oh, you get that. Now think of all of this now. What is A star B? A star B is A minus B all square. So A minus B all square star C. Think of all of this like a I. I think of it like a G. What would be G star C?
G star C,
Yeah, what would be G star C?
it'd be it'd be A, it would be G minus C.
Very good. So if we had G star C, it would just be G minus C all square, don't it? As you said. So G star C would just be G minus C all square. G minus C all square. Now what is G? G in this case is A minus B all square. So that means that G minus C is really just A minus B all square, A minus B all square minus C. A minus B all square minus C, close bracket, all square. All right? And that is what is A star B star C. All right? Good?
Yes, sir.
Nice. So now let's work out our right-hand side now. So let's work out our right-hand side. I'm going to squinch it here. Right-hand side. So right-hand side is A star. What is B star C? What's B star C?
B minus C all squared.
B minus C all square. Very good. B minus C all square. So then what is going to be A star B minus C all square?
It would be open bracket and then another open bracket, B
Yeah.
minus C squared
Repeat.
minus B minus C.
Why would it be B minus C? Remember, you know, A star B. Let's look back at the rule. Look back at the rule. The rule is telling us that the first number is connected to the second number by subtracting the second number from the first number, then squaring it. All right? So now right here, so when we have this, so let me put back the right-hand side. Right here, so we have the right-hand side. The right-hand side we say is A star, B star C. All right, A star, B star C. A star, B star C. So that is just working out to be A star, A star. Now the B star C, as you rightfully said, is the first number B minus the second number C, then we square it. So now A star B minus C all square is going to be the first number A minus what?
Minus C.
Minus what?
But wouldn't it be the opposite of what the left hand side is? So wouldn't it just be
Don't look at the
open?
left-hand side. Remember what you said, always go back to the original thing. When you're working out A star B, always go back to the original thing. All right?
Okay.
So always go
Okay.
back to the original thing. What is A star B minus C all squared? Going back to the original thing. So you replace B with B minus
C.
C all squared. All right? So what would we get now?
So it would be, so we're replacing A star, replacing A into A minus B all squared.
So what I'm saying is, all right, so let me go back to here. I'm saying B stars, A star B is this. So let's use some actual numbers up here. All right, so let's say I asked you, what is 5 star? What is 5 star 3? What's 5 star 3?
It'd be 5 minus 3 all squared.
All square, very good. 5 minus 3 all square. Now what if I ask you what is 5 star 3AXY? What is 5 star 3AXY?
5 minus 3AXY all squared.
5 minus, very good. 5 minus 3AXY all square. Nice. So what if I ask you now, what is X star? What is X star B minus C all square? What is X star B minus C all square?
It'd be X minus B minus C all squared, then another all squared.
Very good. That's it. Yeah, that's it. Nice. So what we're pretty much saying then down here is that what is A star B minus C all square?
So it would be A minus
A minus,
B minus C
yeah.
all squared, then all squared.
Yes, close the bracket, then all square. Very good. That would be it. Now comparing the left-hand side and the right-hand side, is star associative?
No.
No, these are not the same thing. And how you can determine it, you can give them values. So give A, let's say you give A a value of 10, B a value of 5, and C a value of 1. 10 minus 5 square is 25. 25 minus 1 is 24. 24 square is, I believe, 24 square, I can't remember, 576. Now if you try it over here, A is 10, B is 5, C is 1. 10, A is 10, B is 5. So 5 minus 1 is 4. 4 square is 16. 10 minus 16 is negative 6. Negative 6 square is 36. This is giving two different answers. And so we can conclude then that star is not associative. All right? So we can conclude star. So we can say star is not associative. All right? That's good. So star is not associative. That's what we can conclude. So star is not associated. All right, that's question 3. Let's look at a more question. We're gonna get it, man. You're gonna feel so much good when we're done these questions. All right, so question 4, it says, let A be the set of all non-negative real numbers and let star be the binary operation on A, such that for all x, y is inside A, x star y is equal to the positive square root of x squared plus y squared. So is star commutative? Is star associative? And is there an identity element for star? And if it does have an identity, what is the inverse? And provide a reason for the answer. So let's do this question. So I'm getting rid of this one.
Question 4.
All right, so let A be a set of all non-negative real numbers, and let star be the binary operation on set A, such that for all x and y that are in set A, x star y is the square root of x squared plus y squared. Show that star is commutative and associative, and then find out which element is the inverse. All right, so let's tackle this question. All right, so let's tackle this question now. So how we're going to show if star is commutative? We're going to show commutativity. What's commutativity?
That's when the numbers, like no matter the order that you put the numbers in the operation, you'll still get the same answer.
Very good. So how we're going to show that this is commutative?
And I don't remember the formula for the binary.
All right, so for commutativity, we need to show that A star B is the same as B star A. All right? We need to show that A star B is the same as B star A. So you start with your left-hand side, and what's A star B? What's A star B?
Root A.
Square root of?
A.
A.
Squared.
A squared.
Plus B squared.
Plus B squared. Right, so that's A star B. A squared plus B squared. So that is indeed A star B. Nice. Now look what I'm going to do. Now A star B is the square root of A squared plus B squared. But A squared plus B squared it's going to be the same as b squared plus a squared, don't it?
Yes, sir.
I can flip the
So is there
order.
something else supposed to go at the top, like in the question? Because there's another plus after y squared.
Oh, no, no, I did it wrong. This shouldn't be there.
Okay.
This plus should have been before the square root sign. I just copied it wrong there. So now this b squared plus a squared square rooted is the same as b star a, don't it?
Yes, sir.
But then b star a is equal to a star b, which is equal to a right-hand side, and so star is commutative. All right, star is indeed commutative. So star is commutative. Now, since star is commutative, we're nice. So star is commutative. So star is commutative. Star is commutative. Now, since star is commutative, we're good. Now, let's show associativity now. How are we going to show associativity?
Bracket a star b, close bracket star c.
So we need to show a star, bracket a star b, yeah?
Star c
Star c
is equal to a star b, a star open bracket b star c close bracket.
Very good. A star open bracket, B star C. All right, so let's start with our left-hand side. So our left-hand side is A star B. What's A star B?
It would be root
A star
A.
B, as you said, it is the square root of
A squared plus b squared.
A squared plus B squared. That's A star B. So now we need A star B. So find that it is the square root of A squared plus B squared. But then we need to start that with C. So we start with C. What are we going to get?
It would be A squared. So it's the square root and then A squared
It's the
plus b
square
squared.
root of
A
the square root of
A squared plus b squared plus c squared.
very good. It's the square root of the square root of, but then right here, so now x squared. So it's going to be a squared plus b squared square rooted. But when you square a square root, the square root gone. So it just becomes the square root of a squared plus b squared plus c squared. So you're absolutely right. Nice. So it becomes the square root of a squared plus b squared plus c squared. A squared plus b squared plus c squared. All right. So that's what we have. Nice. Now, right-hand side now. What are we going to do for the right-hand side?
It would be A squared. A star.
So we just need to show now A star, B star, C. So A star, what's B star C?
It'd be the square root of b squared plus c squared.
Very good. A star, B square plus C square square rooted. Now what is A star, B square plus C square square rooted?
It would be square root of a squared plus b squared plus c squared.
Very good. So it's a square root of a squared plus b squared plus c squared. So is star associative?
Yes, it is.
Yes, star is associative. Yes, we can conclude star is associative. So nice. Star is associative. So star is associative. So star is associative. All right, now that we show that star is associative, the next part says now, find the identity. How are we going to find the identity?
A star E
A star E
is equal to A.
equal to A. So we're solving A star E equal to A. So now when we solve A star E equal to A, what do we do next?
We would have so the square root of a squared plus e squared is equal to a.
Very good. So we're going to say the square root. So I'm going to write it as A squared. All right, so we have the square root of A squared plus E squared is equal to A. So the square root of A squared plus E squared, and that's equal to A. All right, so what we're going to do next, the square root of A squared plus E squared is equal to A. What we're going to do next?
So we work out a squared plus e squared.
So what we need to do first is square both sides. If we square both sides, what we get is A squared plus E squared is equal to? What's A
Equal
squared
to,
plus E squared?
it'd be is equal to a squared.
Is equal to A squared. So if A squared plus E squared is equal to A squared, what is E?
So e, do we have to take off the square as well?
So when how we gonna find E squared? Remember, we're trying to find E. How we gonna find E now?
We're trying to make e the subject, right?
Yeah, we're trying to make E the subject.
And we're trying to also make e just be e by itself without it being squared.
Yes, yes. So we have A squared plus E squared equal A squared. What we're going to do next?
We didn't have to. We'd have to change it to a square root.
No, not really. First, we need to just subtract A squared from both sides. And so if A squared plus E squared is A squared, then E squared must be 0. That makes sense?
How you
A
got
squared,
0?
how I get 0?
Oh, is it because you bring over a, so a squared minus a
Yeah.
squared 0? Okay.
So E squared is 0. So what is E? What's E? Just 0, right?
Yes, sir.
Nice. So E is 0. Very good. So then the final part asks us to find the inverse. So remember, this right here is the identity. Now let's find the inverse. So I'm going to do the last part at the top right here. Or we're going to find the inverse. What's the equation we use?
A star I is equal to
A star I equal?
E.
E. Very good. So what's A star I?
The square root of a squared plus I squared is equal to 0.
So we get the square root of A squared plus I squared, and that's equal to?
So it would be equal to 0.
0, 0, 0, 0, 0. Very good. So A squared plus I squared is equal to 0. So what's I? How we gonna make I the subject? So first we can square both sides. If we square both sides, what we get then is that A squared plus I square is 0, don't it? When you square both sides, that's what you get, don't?
Yes, sir.
A square plus I square is 0. So if A square plus I square is 0, how are we going to make I square the subject? What's I square?
I squared is equal to negative a squared.
I square is equal to negative A square. So if I square is equal to negative A square, what is I?
It would just I would be negative a.
No, if I square is equal to negative A square, there is no I. So now right here we can say there is no inverse. Tell me why there is no inverse.
Because it's a negative.
You cannot square root a negative number. To find I, what we would have to do is we would have to square root. We would have to square root this right here, but we can't square root negative number, right? Because they tell us it's a real number already, you know, and we cannot square, when you cannot square root a negative real number, all right? So what we notice is that there is no inverse, all right? Easy question. All right, that's it. All right, and
Yes,
these
sir.
are the solution for question 4. Easy. We're almost finished with this worksheet. Oh no, that's the one you're gonna get. Question 5. So they said, let S be the set of rational numbers. Now here what it said now, you know, S is rational. Let S be the set of rationals which differ from -1. A binary operation is defined by, I don't know what that symbol is, but it is defined by that symbol, and it is defined on the S, all right? Where S represents the set of rational numbers which differ from -1. So it means all the rational number except -1. So rational numbers are 4/3, 2/3, all of these stuff, right? So it says determine whether that thing there is commutative or associative. All right? Determine whether that thing in there is commutative or associative. So let's do that now. We're going to determine whether it's commutative or associative. This is the last one we're going to do because they don't put this anymore on the syllabus. All right? Or I haven't seen it since 2008. So I'm guessing that they don't put it anymore. All right? They don't put those ones anymore. That's what I speculate. So let's look at this weird looking symbol for a binary operator. We didn't move. All right, nice. All right, now question 5, let's do this now. So let's find out whether all right, so x, whatever this is, y is equal to x plus y plus xy. Determine whether it's commutative or it's associative. So we're going to show if it's commutative or associative. What we do to show commutativity?
A star B is equal to B star A.
Very good. So we show A star B is equal to B star A. So we need to show A star B. And it's not star. I don't know what that symbol is. Let me try and copy this symbol. All right. So what is this equal to?
B X
It's going to be equal to
B X A.
yeah. All right. So now what is A, whatever that sign B is? Let's call it I don't know. What do you want to call it?
Looks like a X.
Circle X, circle X. So let's call it circle X. So A circle B, A circle XB. What's A circle XB going to work out to be?
A plus B plus AB.
Plus AB, nice. But now we can rewrite this as B plus A plus BA, don't it?
Yes, sir.
And what's B plus A plus BA?
It would be B circle XA.
Very good, that's B circle XA. So that's just B circle XA, nice. So the first part covered. So we've shown that indeed it is commutative. So we can say circle X is commutative. So we can conclude that is commutative. All right, now let's show associativity now. How are we going to show associativity?
It would be it'd be bracket A
Bracket
circle X
A
B
circle X, yeah,
B close bracket circle
yeah,
XC
yeah.
is equal to A circle XB A circle X open bracket B circle X close bracket.
Nice, very good. So let's show our left-hand side now. What's the left-hand side gonna work out to? So we know our A circle XB, we said that it is A plus B plus AB. So we have all of this, A plus B plus AB. All right, and then we have now circle XC. So what's A plus B plus AB circle XC?
It would be A.
So think of all of this as your X now.
Oh, okay. So it'd be A plus B plus AB
Yeah.
plus C
Yeah. Plus
plus A plus B plus AB plus C.
A plus B plus AB times the C.
Or
All
times C.
right. Times the C. Very good. So this is what that works out to be. All right. So we can just leave it as that. And let's see if it's going to give us the same for our right-hand side. For right-hand side, it's going to be equal to,
It'd
for right-hand
be
side, it's A
circle
circle
X.
X, B circle X, C. What's B circle X, C?
It'd be B plus C plus BC.
B plus C plus BC. So then what is A circle X, B plus C plus BC?
It'd be A plus
Yeah.
B plus C plus BC
B plus C plus BC. Yeah.
plus A times
Plus A
B,
times A,
B
A, A plus A times.
B plus
Very good. B plus C plus BC. So now is it commutative? Is it associative? Is it associative?
Yes.
It's associative?
I don't think it is.
Now
I
let's
don't
check.
think it is.
Now look right here. This part is giving me A plus B plus AB plus C. This is giving me the A plus B plus C. But this right here is a AB and this right here is a BC. Can you see the difference now?
Yes, sir. So it's
And
no.
so it is not associative. So circle X is not associative. So we can control that circle X is not associative. Too easy, soft. All right, now let's look at the next part. It says, show that S has an identity with respect to circle X. So we're going to find the identity. We'll find identity.
A circle X E is equal to A.
Very good. A circle X E equal A. So let's solve A circle X E. What's A circle X E?
A plus E plus AE is equal to
AE
A.
equal A. Yeah, so what's E now? How we're going to make E the subject?
It'd be E is equal to negative AE.
All right, so look, these two right here have E in common. So what I want to do is to factor out E. Factor out E from these two and you get 1 plus A. Can you see that? Can you see that?
Yes, sir.
So I factored it out to get E times 1 plus A. A plus E times 1 plus A is A. So now I need to make E the subject. To make E the subject now, what I'm going to do is subtract A from both sides. And so I'm left back with E times 1 plus A. And that's 0. So if E times 1 plus A is 0, what is E?
Is equal to 0.
E is equal to 0. So the identity is 0. Easy, easy, easy question. Soft. Too easy. Now let's do the last part now. Now it says determine the inverses. How do we find the inverse?
A circle X I is equal to E.
A circle X, I is equal to E. So let's find A circle xi. What's A circle xi?
A plus I plus AI is equal to
A
E.
plus I plus AI is equal to E. But what's E?
0.
0. So now let's find I. How are we going to find I?
So we'd factorize out I.
So we can factor it out. So we have A plus factor out I, and we have 1 plus A, and that's equal to 0. So what we're getting now, what we're going to get for I?
I would be equal to 0.
You get I's?
I is equal to 0.
You sure? What are you getting I is 0? Because we need to make I the subject. To make I the subject, why not subtract A from both sides first? So we get I times 1 plus A is equal to negative A. You agree with that?
Yes, sir.
And so what is I?
I would be negative A.
The I is?
I is equal to negative A.
Negative A divided by 1 plus A. You see why it is divided by 1 plus A?
Yes, sir.
We have to divide both sides by 1 plus A. All right? So the only way we're going to do, the only way now, right? So this is the inverse. So that's pretty much all for today, but I have lots of questions for you to do, all right? And I want you to do all of them, all right? All of them, because the practice is really good. The more you practice it, is the more it gets easier and easier and easier, all right?
Yes, sir.
All right, so have to practice them. You have to. All right, so that's it for today. We've covered binary operation. All right, what we're gonna do next week, Friday, is so I'm gonna give you a test to do, but not during our session time because we only meet one time. So I'm gonna send you a Google link. I'm going to create a Google test. All right, well, I'm not gonna create it. I already create a Google test, right? I gave my class at school a Google test on reasoning and logics and binary operation. I'll just share with you that link. And how it is that with the Google link, you only have 1 hour to do the test. All right. After 1 hour, it shut off. The link get closed. So you have to complete in 1 hour. The timer is gonna already be there. All right.
Yes, sir.
And so you do it, and then it grades your test. All right. And so next
Are these
week,
questions going to be similar to the worksheet or the
yes,
homework?
similar to the worksheet questions.
Or the homework?
Repeat.
Is it similar to the worksheet more than the homework?
Well, both of them, you don't
Okay.
find that both of them is the same.
Yes, both of them are similar.
Yeah. They're going to be around the homework and the worksheet. All right. All
Okay.
right. So, yeah. So next week, Friday, we're going to start. Next week, Friday, we're going to start surds, logs, and indices. All right.
Yes, sir.
We're going to look at surds, logs, and indices. Because indices, it's only going to take like 10 minutes to review indices because indices is CXC stuff. Surds, no, surds and logs is what we're really going to focus on. But we want to look at indices as well. All right. So
Yes,
for
sir.
tomorrow, for Unit 2, we'll continue with 6 p.m. just for tomorrow. I'll bump up the time to earlier, but for tomorrow, 6 p.m. All right.
Okay.
So tomorrow, 6 p.m., but we're going to go early on Saturdays. So just for tomorrow, 6 p.m. And also, tomorrow, we're going to complete complex numbers. All right.
Yes, sir.
All right, so you take it easy. Just look out for my email soon. I'm gonna send you an email with all of these notes and a recording of our session. All right?
Okay.
All
Sir,
right.
when would you send the link for the test?
All right, so I'm gonna send it about I want you to submit this first. So I'm going to
Oh,
send it
do the
about midweek.
binary homework first?
Yes, so I'm going to send you, when I send you this binary homework first, if you can send me the homework by about Wednesday, then I can send you the link Wednesday, same day, or Thursday.
Okay.
All right. All right. Yeah. All right. So take it easy and I'll see you tomorrow.
Okay, sir. Take it
All right.
easy as well.
All right. Yeah.